Well, so let's take a look at Chapter 5. Chapter 5 deals with equilibrium of a rigid body. So we started talking about how forces acting on a rigid body react in Chapter 4. So we looked at adding the concept of moments. When we start to deal with equilibrium of rigid bodies, the first place we want to start is to look at how the rigid body is attached to the world. So there are some common ways to attach bodies to the world. One of the ways that you might see is a hinge or a pin reaction, typically drawn like I've drawn it here. So what you need to do when you see one of these is you need to figure out what types of forces, reaction forces, are resulting because of the connection to the world. So for a pin force, how can we move it? Well, we can flip-flop a pin or a hinge back and forth, right? If you walk up to your door, you can open, you can close the door. It has a moment that it's free to move along that axis for a moment. Otherwise, it wouldn't work as a hinge. However, right, you cannot move it in the X or Y direction, right? If you try to pull it or push it or in either direction, you're going to have a reaction force associated with it if it is an effective hinge or pin. So with a pin or a hinge, we have an AX and an AY reaction as shown here. So another type in 2D that we might see is a rocker or a roller. The roller essentially looks like a pizza cutter, right? A wheel that, picture a pizza cutter, right? A wheel that you can wheel across your pizza and cut into slices. With that type of wheel, right, you can pick it up off the table, you can roll it across the table, right, but you can't push it down into the table, right? So the only force for either a rocker, a reaction force for a roller or a rocker, is a normal force, an AY direction force. It pushes, the table pushes up when you try to push down. A rocker, if you took your fist and held your arm out and leaned up against the wall with the fist, that's kind of a rocker, the way that your fist can move. Right? You could rock your fist around, but you can't be pushed into the wall any farther, but you could be pulled away from the wall, or somebody could hang a weight on your hand and it would fall down in that particular case. You might see the roller also as like a roller skate in this particular case. You'll see it drawn like this. And same thing, you've got a normal force reaction. You can pick it up off the ground, you can roll the thing back and forth, but you can't push it down into the ground. One of the last types of connections to the world is this cantilevered beam reaction. So it can be horizontal or it can be vertical. The vertical type is if you picture a telephone pole outside your house or your mailbox post. Right, something holds it into the ground and there's a post that comes up from it. The horizontal one is like a shelf. If you picture going to the grocery store, like there's shelves and there's products stacked up upon the shelves. So what type of reaction forces can you have? Well, a cantilever beam shouldn't move in any direction, right? It shouldn't move in the X direction, it shouldn't move in the Y direction. And if you put a force on the end of it and try to push down or pull on it, depending on which direction the beam is associated in, there should be a moment reaction to prevent the thing from collapsing or falling over, depending if it's horizontal or vertical. So there are three reaction forces, an AX, an AY, and a moment force for a cantilever beam. So with that in mind, right, if you remember when we got to Chapter 4, we introduced this concept of moment. Right, so we're going to take that one step farther in Chapter 5, and we're going to now have three equations. Right, so in a 2D case, we have this arbitrary point O, which is typically called, and we can apply three equations at that point. We can apply an f of x equal to 0, f of y equal to 0, and moments are equal to 0. Again, if the body is in equilibrium, right, all of those forces will come out to 0. Those are our equations of equilibrium. So what we're typically going to do when we're given a problem and I've kind of mentioned this a few times before, is you're going to create a free body diagram. So in this particular example, right, there is a cantilevered beam, and it's laying horizontally, and there's a 1200 Newton force that's 2 meters from the edge. So the first step would be to take the idealized model or the real life model and convert that to a free body diagram. So you always get rid of the connection to the world. So the brick wall gets erased. It is a cantilevered beam, so what you do is you replace that with the reaction forces. So remember, cantilevered beam has an AX and an AY and a moment at that point A for that connection. Right? You shouldn't be able to pull it out from the wall, you shouldn't be able to push it down, you shouldn't be able to lift it up, whichever. You can't move in any direction, typical. If the weight is negligible, which it doesn't say here, then you can neglect the weight. However, in this particular case, it looks like that the weight of this beam is 981 newtons, which is pretty large compared to the force that's being applied. So the weight is always applied to the center of gravity, which for a rectangular shape is dead in the center of it. So you draw your shape, get rid of the wall, or get rid of the connection to the outside world, add your external forces, your reaction forces, your external forces, and let's see what the last step they tell us here is. Label the loads and dimensions on the free body diagram. Right, once you get to that point and you've got your free body diagram, you apply your equations of equilibrium and you can solve for your unknowns. Simple as that. One of the other concepts is this two-force member concept. So you can have a force. It's pretty simple when it's a link. This happens to be a bent link in this particular case. So if you look at this bent link, if this link is in equilibrium, right, then the force on one side has to equal the force on the other side. The lines of action for those two forces are on the same line of action. So a two-force member has the same force on both sides when it's in equilibrium. So in this case here, you got an FA and an FB for the two sides. The FA and the FB have to be equal to each other because, again, there's no other place for a force to be applied here, and this thing is in equilibrium. Some examples. The hydraulic ram is the one there on the right. It's a pretty common example, mechanical example, right? The force on one side of the ram is the same as the other side of the ram. That link there in the bucket looks similar to the little sketch that they have there, right? So that little bent boomerang type link, right? The force at A is equal to the force at B because those are two force members. Going to become a little more important when we get into chapter 6, but to be able to identify those now helps to simplify your problem as you move forward. When we get to frames and we get to trusses, it becomes much more important. So here's how you're going to solve a 2D problem. If you don't have a XY coordinate system, add one. Add it in a way that makes it easier to solve the problem. Put some of those forces along the X or Y direction if you can. Draw your free body diagram. So you get rid of your connection to the outside world, add your forces in, label all your forces, boom, you got your free body diagram. Then you apply the three equations of equilibrium to solve for the unknowns. Right. Simple as that. Now, some caveats. There can be systems where there are more unknowns than equations. How many equations do you have in 2D? You've got 3 equations. So if you come up with 4 unknowns, you can't solve it. So you have a system that is what's called statistically indeterminate. You can't solve it. You can also, right, the equations are listed as the sum of the forces in the X equal to 0, the sum of the forces in the Y, the sum of the moments equals 0. You can solve those in any order. And sometimes when you see the equations and the unknowns, it might be easier to solve them in a different order. Whatever way you decide to do it is fine. Do it the easiest way first. Don't come up with the hardest way to do it. And then, most importantly, and I've mentioned this a few times in some of the classes, a negative answer means the direction is opposite of what you chose. So when you drew your free body diagram, you put directions, you put arrows, you put directions on all your forces. If you run through the answer and you get a negative answer, whatever direction you assumed at the beginning was wrong. So you just got the wrong direction. So change your direction, or leave it as a negative answer with the other direction, and both of them are reasonable. So 3D support reactions, very similar. You just got some different types of supports. So you got that smooth surface support, right? That's kind of like your roller or your rocker in the 3D world. Right? There's a normal force. You can move it all over the place, normal force. The ball and socket. A ball and socket is essentially like your shoulder joint. Right? You can spin your arm around in circles. You can put your arm in front of you and behind you, of course within limits. But you can't pull it away from you or push it up or push it down, push it in, right? So you've got Fx, Fy, Fz reaction forces. The journal bearing. So with a journal bearing, that shaft can actually slide through the bearing. Typically there's some kind of mechanical stop that's usually put on there so that doesn't happen, because obviously you wouldn't want that to happen in a real system, but it can slide through. So it can spin, of course, because it's a bearing, it's supposed to spin. It can slide through. However, in the other two directions, right, you better not be able to move it in those other two directions or spin it in those other two directions, or something is seriously wrong with your bearing. And we talked about a hinge already before, right? A hinge has a moment around one axis, the axis where the pin is. Every other direction you should not be able to spin it or move it as shown there. So you got all those reaction forces associated with a hinge or pin. So what can happen is a real system can have multiple sets of bearings or hinges, and some of those forces can fall out. So for instance, right, in the case of the one on the far left-hand side, let's look at that one first. Right, you got a couple of bearings, and those look like they're probably sleeve bearings in those particular cases. So you can pull them out or you can spin. Right, well, you can't actually spin in this particular case because the other two bearings prevent the thing from spinning. So that can happen in a real system, right? You can have hinges and have something else or a pin that prevents that from actually moving. There probably is good reason to do that, but I don't know. The one on the far left kind of looks like plumbing to me, right? If the plumber runs the plumbing through the house and you don't want the pipes to move, so as the pipe moves, they put those supports on there. The other issue that you can have, I guess that's another slide. So now we have, when we move to 3D, we have now 6 equations. So we got the sum of the forces in the x, the y, and the z direction equal to 0. We can take a moment around each of those axes also. A moment around the x, a moment around the y, and a moment around the z equals 0. So now in 3D case, we can have up to 6 unknowns because we have 6 equations. Right? If we end up with 7 unknowns for some particular reason, we can't solve it. So that is the message behind this particular next slide. Right? In this particular case, you have a problem that has more unknowns than equations. Right? You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It looks like there's 12 unknowns in this particular case. right? You've got 6 equations. You cannot solve this problem. It's statistically indeterminate. Could this be used in practice? Yeah, it might be used in practice in real life because there might be forces that don't always act on the system that have to be considered. For instance, up north, right, there are these collar ties on the trusses in the ceiling of the house. Their only job is for snow and ice loads. So during the fall, the spring, the summer, when there's no snow or no ice, they do nothing. But during the winter, if you get a really heavy snowstorm and there's snow and there's ice, those extra supports provide the support to keep the roof from collapsing because of that extra weight. Oh, and here's the last slide, the last thing to kind of consider. You can have, especially in 3D cases, improper constraints. So look at the top one. You've got, on both sides, you've got a ball, right? Balls can move in each direction. So what happens with that force P? You apply that force P, and that whole bar is going to fall, right? So there's nothing to actually prevent a moment in that particular case. It's an improper constraint for the force that's being applied. The A-B thing is kind of like, if you remember I just said it like 2 minutes ago, if you put your fist up against the wall, right, that is like a rocker. So B is kind of like, I put my fist up against the wall and I'm standing with my arm straight out, right, horizontal from my shoulder. If you start to hang weights on your wrist while you're doing that, there are a certain amount of weights that you can probably hold, but if somebody came and hung 200 pounds from your wrist, what's going to happen? Your hand is going to fall down, right? There's no constraint to keep your hand from falling. That's what we have on the lower drawing there. So there you go. There is an overview of Chapter 5.